Good morning, all. Again, today is the application week before the midterm exam. We are gonna solve a few examples today. Let me share my screen first. Okay. What is this? This problem. Yes, okay, it works. Now, okay, here we have the first example. Okay, we have a stick like this, and all the sections are circular. Here we have a circular section and another circular section here. We apply a P here, axial load. The diameter at this portion is D1. D1 equals 26 millimeter. Here, D2. Second. Here, D2 is 20 millimeter. So the length of the portions, we have 3 portions here. This is the first portion, which is 0.1 meter, and this portion is 0.3 meter, and again 0.1 meter. Totally, it's 0.5 meter. Okay. The other data here is the modulus of elasticity for the material of this stick and frame, whatever. E is 10⁶, and sigma allowable equals okay. This rod, this member, this rod makes 0.12 millimeter elongation under the load P. Okay. So please calculate the maximum load P and
and the maximum axial stress under this load. Okay, the question is this. Here we have a stick. So, and there's a P load, and under this loading, there's an elongation. We know the total elongation, 0.12 millimeter. So calculate the load P on which provides this elongation. After that, calculate the maximum axial stress on the member. Okay. Okay, what can we say for this type of loading? This is an axial load. Okay, we know that. The first thing, axial load. It's coming from question, or we can understand directly because the loading is perpendicular to the frame section. Okay, this is axial load. We know this. And the second thing, we know that if there is an axial load somewhere else, there's an elongation, right? We talk about these rules. If there is an axial load on a member, there is an elongation. So what was the elongation equation? Let's say the elongation is delta P times L, the length of the member, over E times A. So here, if everything is same, if this portion is completely the same, and if L goes up, the elongation delta goes up. It's same for the P. Let's say here, if this portion, all these numbers are constant, if P goes up, delta goes up. And the opposite is works for the bottom portion. If we have higher E times A, which is here, we are gonna get lower delta. You have to understand this equation, but this is a basic equation. It's not difficult. If you know this equation, you can solve the problem. Let's write the total elongation equation for each portion. Here you can see when you look at the section or frame, there are 3 different portions. Okay, due to the geometry, you have to consider this one. Okay, you have to consider in the equation. Let's write the equation. The first portions. By the way, let's calculate the areas. Maybe that works for us, because, or directly write the equation. No worries. Let's write this portion. P is P, the axial load, times L. L is here, as you can see, 0.1 meter. 0.1 meter. This is in meter. Let's have a look to modulus of elasticity. It's in centimeter. Let's convert this meter to centimeter. 0.1 meter is 10 centimeter. Let's write it here. 10 over E. E E was given in the question here, 10 power 6, 10 power 6. Here we go, 10 6 times what? Area. Area is easy. By the way, I say this easy, but sometimes you do everything, but you can't calculate the circular area. Please take a look at this. It's easy. It's this knowledge is coming from the high school. The area of this circular portion. So P times I'm gonna convert this millimeter to centimeter. 6 over 4. Okay. This portion is area. Okay. Here, this is E. Oh, okay. Let's go ahead. Now, for the second portion is here. Okay, let's write. By the way, at the end of the day, P is constant all over the section. What I suggest you before to start the calculation, draw the axial force diagram. It's like this. Okay. This is the axial force diagram. The P is constant everywhere, all along our member. Okay, let's write it here. The P again, P times total length. Total length of this portion is 0.3 meter. It's 30 centimeter over. E is E times area. P times 2 square over 4. Okay. This is the area again. This portion is area. Plus the last portion. When we take a look this one, by the way, I completely forgot to give the diameter here. Diameter here is D1 again. Okay, D1. Okay, D1, it's 26 millimeter. It's completely same as the first portion. What you can do, you can put the beginning of this equation, you can put here 2. That's okay. But I wanna write the equation again. I'm gonna write the same equation. No worries. You can put here 2. That's it. Or you can write the equation again. Let's write the equation here again. P times 10 over elasticity here. The area P 2.6 squared over 4. Okay, equals what? This equals the total elongation given in the question. Where is it? It's here in the question. 0.12 millimeter. Okay. This is millimeter. All the equation, in the equation I use centimeter. We need to convert it to centimeter. 0.012. Okay, this is centimeter. So we have one equation. Everything is fine here. We have only one unknown, which is the P. If you solve this equation, so I guess you can do it. You have your calculators, and so you can solve the P. By the way, don't forget this. For P, the number, by the way, this is load P, this is the P, you know. For this P, use the calculator P key, okay. Don't assume that is 3 or 3.14. No, please use the calculator, what it gives to you. That's it. Okay, from this equation, solve the load P, which is gonna be, let me see the result. 0. By the way, everything is in kilogram. In kilogram. Okay. This is the total load P. Now we have the load P. Okay, we solved this portion. That's okay. In the second portion of the question, the maximum axial stress under this load, the load is P here, 900 kilograms. That's okay. When we look at our member, where can we find the maximum stress? Remember, if we are talking about stress, the general equation for stress, let me write here stress is force or area. Depending on the direction of the force, this stress will be axial stress or shear stress, right? If our force is perpendicular to the cross section, it's axial stress. If the force is parallel to the cross section, the stress is shear stress. We know this. This is the basic equation we have to know here. Okay, we are looking for the maximum stress. On this member, the force is constant everywhere, right? As you can see, P is P all along the member. So to get the maximum stress, we should look for the minimum area, because we know that if this area goes down, stress is gonna go up. So we need to find the minimum area. By the way, if you can't do this, if you can't decide where you should look for, calculate the axial stress for each portion. Okay, if you don't decide for this portion, and for this portion, calculate the axial stress and select the maximum one. But basically, if the load is constant everywhere, the minimum area gives us the maximum stress. So when we take a look this member, this portion, in this portion, we have the minimum area. Okay, we have the minimum area. So let's come here. The axial stress, sigma max, is what? 900 kilogram. The area is here, P times 2 square over 4, because it's circular. And here the stress is 286.50 kilogram centimeter square. That's okay. Is it safe or not? The structural member is safe or not? This is the question. How we can decide that? Yes, we have the maximum stress. We have to compare this maximum stress with the sigma allowable. In the question, you don't have to know, you don't have to memorize this allowable stress. So let me change color. What is it? 700 kilogram. So the calculated stress, the maximum stress is less than the allowable stress. That's why this member is safe. Okay. This is the question 1. Any comments or any questions so far? Is everything okay? I hope it's okay. So another one. Yes, here we have. If it's okay, I'm gonna jump to the next one. Okay, here is the second question for you. We have a bolted connection here. And thicker plate at the bottom. Okay, here we have P node. I don't have the answer of this question. We are gonna solve it together. I have the question, but don't have the answer. No worries, we can do it. 8 millimeter. Here is the 10 millimeter. We have okay. We have 5M16. Okay, the plan view of this connection. Here we have, it goes here and here. Okay. Let's say this plate and this is the other. Here we have 1, 2, 3, 4, 5 bolts. Okay. And 4 bolts allowable equals sigma L allowable for plate, for steel plate. sigma allowable 1.40. Calculate maximum P. Okay, this is the question. Here we have two plates and bolted connection. You can see the thickness of the plates, 8 millimeter and 10 millimeters. We have 5 M16 bolts on this connection. So remember, for bolts, we have two cases. And if we go to the plate, we take into account the axial load carrying capacity of the steel plate. Okay, so now let's get started from the bolt. Let me change my color to this one. P toe. Okay, let's have a look at this connection. We have only one touch surface, right? One touch surface. So number of shear plane is 1 here. It is 1. Okay. And the area of the bolt, the 16, I'm going to convert it to centimeter because this is, remember, when I give you M16, the diameter here is, let me write it here, where? Diameter of bolt is 16 millimeter. Okay, diameter of the hole is 16 plus 1 millimeter, so it's 17 millimeter. Don't forget these two ones. Let's go back. P times 1.64. This is the area. This is the area for the bolt. Okay, area times the allowable stress for shear gives us the capacity of that bolt. The allowable stress here, 1.12. Okay, 1.12. This is the capacity for the one bolt. So actually calculate the maximum P load is the maximum capacity of this load. So we need to consider the number of bolts. Let's take a look to the plan view of the connection. How many bolts we have? We have 5 bolts. Okay, we have 5 bolts. So this is the total equation to calculate the all shear capacity of the bolts. Now we are gonna do it. I'm gonna get my calculator and then we will do this calculation. That's okay later on. Let's write the equation for bearing. D, remember, it was about the cross-section area of the bolt, remember, let me draw it here. If I have a section like this, the mid section is this. We calculate this area. This area bear the plate, the total, the maximum area of the bolt. So the area is here. This is the D. This is the T. Which T? The minimum T, because if we have that means if we calculate the minimum area, we are gonna have the maximum stress. That's why we check that point. So this is the mean. Let's write that to equation. The area is D. You know, D is D. Given in the question, 1.6 centimeter. Centimeter, I converted it to centimeter, not millimeter here. Times T mean. We have two plates here. Take a look, the plate goes right and the other plate goes left. Here we have 8 and 10. Minimum is what? Minimum is 8. Okay. Converted centimeter. D times T mean. This is the area times allowable stress in the question. 2.4D. Okay. This is the bearing capacity of the one bolt. Okay. Bearing capacity of the one bolt. Now write the total number of the bolts here. Okay, again, we are going to calculate this at the end. Okay. Okay, now we have the bolt capacities. Bolt capacities. Or we can calculate them now. Let me calculate it. I don't have the results. That's why I'm gonna write the equation. Where is my calculator? Here we go. Yes. 1.6 square times P times 5 over 4. Here, the result is this one. And calculate the same for the bearing. 1.6 times 0.8 times 2.4D times 5. Okay. Let me do it again. P, no. 1.6 square times P times 5 over 4. Okay, the calculations are right. These are the shear and bearing capacities of the bolt. Let's calculate the axial capacity of the steel plate, P steel, P plate, whatever. Okay, now I'm gonna ask you the critical question. To find the maximum capacity of the plate, which section I should consider? We have, for example, we can cut from here. This is 1, 1. This is, I can cut from here to 2 and this is the 3, 3. In the first section, we have a solid area. There is no opening, any void on the section. So it's a total area. That's okay. In the second section, we have only one bolt. There is one bolt void on the cross section. In the third one, there are 2 bolts and there will be 2 missing bolt area over there. So here, the critical thing is you have to consider the minimum area. Okay, minimum area gives the capacity of that steel plate, because the weakest point on this steel plate is where the maximum bolts are located, which is the section 3. Okay, which is the section 3. Now we are gonna consider the section 3. Okay, this one. Here area times area and the thickness is the minimum thickness, you know, because 10 has the more capacity than 8. So we're going to consider the 8mm plate. Okay, let's calculate the cross-section area of this plate. By the way, I forgot something to give you, which is this one. The width of the steel plate, which is 180mm. Okay, 180mm. Now it's here. Let's write the equation. The 80 centimeter minus 2 times what? Remember, here we have 2 bolt holes. When you cut from here, there will be missing 2 areas. So 2 times this one, 1.17 centimeters. Okay. Times, this is the width. The thickness is 8mm, 0.8. Okay, 0.8 here. Now, here is the area. Cross-section area of the plate. Okay, times. The area times allowable stress gives the capacity. Allowable stress is given in the question again, 1.40. Okay. Now let me calculate this one. Okay, here we go. Clear. 18 minus 2 times 1.7 times 0.8 times 1.4. Yes. The result here is 16.35 tons. Now we have the capacity of balls for shear and bearing and the plate capacity for this connection. Okay. What is the capacity of the connection? Now, let's decide that one. Okay. Till here, what we did, we calculate the capacities separately. We know all we know all the capacities. Which one is my connections capacity? We have to decide this. Actually, you can calculate all these capacities, but if you don't decide the correct capacity, everything is wrong. Because your structure will fail, your connection will fail. That's why you have to be careful while we are deciding the total capacity of the connection. Okay. What do we do? Let me write it here. P connection. Okay. P connection. Okay. The logic is basic, right? Here, let's say we have a connection here, right here, basically. The shear capacity here is bearing capacity and the steel plate capacity here. Let me write it here. Okay. I'm trying to give you a logic. I know the most of you will make a wrong decision in the exam. Okay, I'm gonna ask this question in the exam. So please think about the logic. If you can see the capacities 11, 15, and 16. If I apply, let me write here, 10 tons. What do you think? Is this safe? Yes, it's safe because this 10 is less than all these capacities. That's okay. Instead, if I apply 16.35, this one is the safe for this connection. Okay, when I apply this 16 to the connection, it works for the steel plate. Steel plate is safe. There is no problem. But take a look to other capacities, shear and bearing capacities. One is 11, other is 15. So the bolt capacities are less than the steel. So till we get this 16, when we apply this loading to the connection, when we get the 11.26, the connection will fail. You're not gonna see the 16.35 on this connection because the minimum capacity governs the connection. Minimum capacity. When you apply 16, it doesn't go to 16 because here there is 11. You are increasing loading. When you reach to the 11, your connection will fail. So at the end of the day, you don't have a capacity like 16. The minimum governs the capacity. That's why for the connection capacity, you have to consider the minimum one. Minimum. Okay. What we have? This one, and minimum here is 11.26 tons. Okay. This is the capacity of the connection. Okay, this is the, what is this? Yes, this is the capacity of the connection. So when you have this type of connection, please decide where you are gonna cut the steel plate. So which cross-sectional area you are gonna calculate. The section is where you have more bolts. Okay, we just cut the section from there and calculate the area and do your question. And the second thing, most of you will gonna do this mistake in the exam. While you are calculating the diameter of hole, don't do this. You can do two things. The correct one is this one, right? As you can see, everything is in millimeter, but most of you is gonna do this. You know, this is the diameter of bolt, it's in millimeter. You're gonna do like this, 1.6 centimeter plus 1, and you're gonna have 2.6. Okay, this is wrong because this whole diameter, the extra 1 millimeter is in millimeter. If you do it like this, you're gonna have 2.6, and at the end, you're gonna calculate the steel plate capacity wrong. Okay, this is not correct. Do it everything in millimeter and then convert it centimeter where you need. Okay, this is the case. Okay, guys, I think let's have a break now. Half an hour. It's 10 o'clock now. So in the next session, we are gonna solve 1 or 2 more problems, and then we are gonna close the session. Okay, let's have a break. See you guys. Can you hear me?
Evet hocam.
Bir önceki soruyu duydunuz mu arkadaşlar anlatırken?
Yok hocam, ses yoktu ya benim bilgisayarımda en azından.
Diğer arkadaşlar da mı bu şekilde? Bir kişi daha bana bir cevap verirse. Yok, bir de anlatacağım da. Okey, o zaman bir kere daha anlatalım onu. Şöyle yapalım. Neden anlamadım ya, bir problem var zaten de. Bir daha anlatayım arkadaşlar. Sıkıntı yok. Okay, here we have a simple beam. On the simple beam, there is a uniform distributed load. The magnitude is 1 ton meter, and there is another concentrated load, which is 4 tons. By the way, this is ton. We are gonna draw the axial force, shear force, and moment diagrams. Okay. Firstly, the first thing first, we are gonna calculate the support reactions. If we write the total x0, you see there is no horizontal load on the structural system. That's why HA, the horizontal support reaction, is 0. Okay, this is 0. And then we write total MB. Total MB, by the way, B is here, A is here, you know, I guess. We calculate the moment around the point B, VA times 5 here, minus 4 times 3, the moment coming from the point load, minus 5 times 2.5. This moment is coming from UDL. Okay, equals 0. If you make this solution, you're gonna get this one. VA is 4.9 tons. Okay, I wrote it here. Yes, here we have total MA equals 0. VB times 5. I made the assumption this direction is positive. Okay. VB times 5 minus 5 times 2.5. This is the UDL's moment. And this is the concentrated loads moment. Minus. Why? Because they're in the opposite direction of my assumption. That's why they are minus. So the totally it's 0. From here, VB comes 4.1 tons. Okay, 4.1 tons. So I wrote the loads here. Now let's have a look to axial force diagram. When we look at the system, is there any horizontal load which makes an axial load on the system? No, because at the beginning we calculate HA 0. So there is no axial force. We draw, if there is nothing on that member, we put a 0 on the diagram. Okay, that's easy. Let's do the shear force diagram. We are going to start from here. This is the start point. At this point, we have a concentrated load. Support reaction is a kind of concentrated load at this point. Okay, so we apply it here. It goes up. The arrow goes up. I'm at this point, goes up, and put here the 4.9. We are now in the positive side, 4.9. So in this purple area, so from this support to concentrated load, there's only uniform distributed load. Take a look at this purple area, calculate the area of this uniform UDL. So the area of that UDL is the magnitude of that portion. 2 times 1 is 2. The concentrated load here is 2. So the arrow goes down. At the beginning, we went up. Now we are gonna go down 2. So 4.9 start point is this, and go down to it's 2.9. Since this is the uniform distributed load, we connect these 2 points with 1 degree curve, which is a linear line. We connect these 2 points line. Now I'm at this point. Okay. At this point, there is a concentrated load in the vertical direction, and the concentrated load goes down. As you can see, take a look to arrow, red arrow, which goes down. I'm here now. So I'm gonna go down 4. Okay, go down 4. I will go to the negative side. That's okay. It's 1.1. I put the negative sign here. Okay. Remember, if there is a concentrated load on the structural system, that means there is a sudden change on the shear force diagram. Now, we have just completed the concentrated load. At the right-hand side of the concentrated load, what we have only uniform distributed load. The pink area, the pink shaded area, calculate the magnitude of that portion. It's easy, again, 3 times 1. That means 3 tons. I'm here at minus 1.1. I'm gonna go down 3. So 1.1 go down 3, which is 4.1. Okay. Again, since this is the uniform distributed load, I'm gonna connect these 2 points with a line, 1 degree curve, a linear curve with a linear curve. So we have just connected these 2 points to each other. Now we have the shear force diagram. here. To draw the moment diagram, we are going to use the area under the shear force diagram, as you know. At the moment diagram, this is my start point. And the moment at this point is 0. Why? Because it's simple support. That means a pin support. This is a simple beam. It's a pin support. Pin support. There is no moment on the pin supports, as you know. So the moment is 0. So we are going to calculate the area under the shear force diagram. Take a look at the area shaded green here. The area calculation is given here. This is a trapeze section. It's easy. This plus this 1 over 2, the average of these 2 lengths times the distance here. It's easy. If you make this calculation, you are going to see this is 7.8. So this is the point, 7.8. So we have to connect this 0 start point to the 7.8. Remember, we always increase the degree of the curve. We increase 1 more the degree of the shear force diagram. Shear force diagram degree is 1 degree. So we're gonna use a 2 degree curve here. Actually, we don't know the actual curve drawing. That's okay, but you can make a curvy drawing here. But don't forget to write here. This is the 2nd degree curve. That's okay. Now we are here. And in this portion at the right-hand side of this point load, there is an orange shaded area. We need to calculate this area. See the calculation. It's easy for you. It's a geometrical calculation, basic. It's 7.8 and in the negative portion. That's why the area will be negative. We are going to reduce this total moment. You know, this is 7.8. So this is 7.8. We are going to go back to 0 at this portion. Is it correct? Yes, it's correct, because at this point we have a roller support. Roller support means there is only vertical support reaction. There is no moment at this point. Okay, there is no moment. That's why we are doing correct. So we have to connect this 7.8 to this point B. How? Since there is again a linear curve over here, we are going to connect. We are going to use second degree curve. Let me write it here. Second degree curve. This is the moment diagram of the structural system. Okay, moment diagram of the structural system. By the way, here there was a rule, remember, for the shear force diagram. When the shear force diagram goes from the 0, at this point, there is maximum moment value. As you can see, at this point, we have maximum moment value. Okay, this is the axial shear and moment diagram, axial force, shear force and moment diagram of the simple beam under given loading condition. Any questions so far? No. Okay. I'm gonna solve one more question. It's a little bit complex than this. Here we go. Now let me see the question here. This is the fourth question. I'm gonna solve a frame. Question is here. Okay. Just a second to maybe I can find it. Yeah. Okay, we have a frame here. Here we have a pin support. A roller support. And what we have more, here we have concentrated load, one more concentrated load, and also uniform distributed load. This is 8 ton. This UDL is 5 ton meter. The distances here, this is for the first 8, this is for the second 8 meter. 2 meters, 2 meters, 2 meters. Totally, it's 6 meters. The height of the system, 3 meters. Okay. So we are gonna draw the N, T, M diagrams here. Now, we have, let's put here okay, the first thing first, don't forget the sum. When you get a structural system, you are going to calculate the support reactions first. Okay, support reaction. I'm gonna write directly the support reactions now. You can calculate it easily. I know because it's not the main subject of this course. The support reaction was the subject of the statics course. That's why I'm gonna write the results here. But you know, write the total X, total Y, or total MA0, total MB0. Okay. You can write these equations. Now, HA is 4 here, vertical A here, 21 ton, vertical B here, 25 tons. Okay. Now, we have the all loadings on our structural system. Okay. By the way, when we start to draw the internal force diagram, what we do first, by the way, this is the wave direction. What we do, we draw the positive directions here as a reminder for us. If the axial force goes out, this is positive. If this goes down, this is T. At left-hand side, it goes up. And this is the moment positive. This is the moment positive. Okay, this is the moment positive. So here, this is a reminder. I suggest you to always draw these positive directions when you start the calculation. Now we are going to do the axial force diagram. Axial force diagram. Okay. So here, what is the axial force? What is the axial force? So at the end of the day, I'm gonna make some calculations here. You can see that directly. That's okay. If you can do this, yes, do it. But if you can't see what the magnitude of axial force over here, remember there is a support here, 21. I have a small portion. I cut the system from here. This is the wave direction. Is this the cut from right-hand side or left-hand side? It's right-hand side, because if you take this and put there next to it, you are gonna see this is right-hand side. So the axial force goes like that. Okay, goes like that. Here, n plus 21 equals 0. N is minus 21. Actually, you can decide it's 21 by just looking this structural system, but be careful. It's minus 21. There is a real big differences in between positive 21 or negative 21, because if there is a positive axial force, that means tension. If there is a negative value, that means there's a compression. That's why there is a big differences. If you don't decide the sign of the force, cut the system and write the equation. It doesn't take time. It takes 5 seconds maximum to do this. That's why here we have minus 21 on this column. Okay, on this column. From here to this point, there is no another vertical load. As you can see, we changed the axial loading. axial loading. So it's constant from this point to this point. The axial force is 21, but minus 21. Okay. By the way, I completely forgot something on the question. Nobody asked me how you calculate this for. There is one more loading at this corner. Okay. There is one more loading at this corner. This is 4 ton. That's why this is 4. Okay. Now that's correct. Now we are on this portion at this corner. What is the axial force at this point? You can decide it easily, right? It's easy to see that, but if you can't do it, cut the system from here. This is the column. This is the small portion beam. We cut the system from here. What I have horizontal 4 in this direction, 4. So I don't know what the axial force at this point. Let's write it n minus 4 equals 0. So n equals 4 tons. So here at this corner, my axial force is 4. Here 4. That's okay. But all along the beam, is there any other loading which changed the axial load in horizontal direction till this point? No, there is nothing. So that's why what we have the positive. Let me, here is positive. I have 4 all the way. I have same axial force. Now take a look the column here. Take a look the column at the right hand side, this column. So there's a support reaction. That means there's something axial force. There's some axial force on the column. If you can see it, write it directly. If you can't, write the equation. Okay, let's cut the system from here. I suggest to cut because sometimes when I do all these calculations in my mind, I can calculate the magnitude easily. That's okay, there is no problem. But when I do this calculation very fast, I can make mistakes on the sign of the force, positive or negative. Instead, I always write the equation. I waste maximum 5 seconds to do it. As you can see here. Here we have 25. This is n. So write the equation for this. N plus 25 equals 0, n equals minus 25 ton. Okay, that means the axial force on the column is minus 25 at this point. Okay, this is minus 25. Let's write it here. This point is minus 25. Take a look at the column. Is there an axial force which affects this total in the vertical direction from here to this point? There is nothing. That's why the axial force at this corner is also 25. Connect them to each other. This is minus 25, 25. Okay. Now this is the axial force diagram. Axial force diagram. Okay, let's do the shear force diagram. Okay. We are going to start from this support reaction, this support. So as you know, the shear force where the force is perpendicular to frame member. Okay. At this point, at support point, cut the system from here again, from here like this, take it out, positive direction. So when we take this and put it here, it's positive direction. Okay, don't forget this one. While we're cutting the system, we have to consider to right side cut or left hand side cut. This is the right side cut. That's why this is the positive direction. This is T here, but in the system I have 4 as a support reaction. That means T equals 4 tons. Is it positive or negative? It's positive, as you can see here. It's positive. So we have a shear force 4 here. Okay, from this point to this point. Is there any other horizontal force which affects the shear force? No. So until this corner, it's constant. I'm going to do this like this. It was positive. This one. Now we have completed the column. First column. Let's do the beam here. Beam here. At this corner. Cut the system from corner. What I have 4 at the support point 21. 4. We are talking about the shear force. Shear force, is this a right cut or left cut? Right cut. It's same as you can see. We are going to take into account this portion. The shear force goes. So what we are going to do, this 4 doesn't work for this beam because it's in the axial direction. This vertical 21 is perpendicular to beam. That's why we consider that force. So T minus 21 equals 0. T is 21 tons. It's positive. It's positive here. What I have a 21 at this point. Okay. On this beam, is there any other the perpendicular load which changed the shear load? Yes. All these external loading which are perpendicular to my frame member. So they change the shear force diagram. Okay, that's okay. There is no problem. But when we look at the structural system, there are 2 concentrated loads here. 2 concentrated loads. Okay. By the way, the frame here is, this is the frame. Okay. This is the frame. The others. Here. This is the frame. And this is the shear force diagram. So from, I'm at the corner, from here to here, there is uniform distributed load in this purple portion. Okay, consider them. Calculate the area. 2 times 5, which is 10. 10. Okay. It goes down. It goes down. As you can see, the arrows looks the downside till this point. it goes down and 10, it's gonna be 11. Why I've just connected these 2 points with a line, because since there is a uniform distributed load in the purple shaded area, the shear force diagram is linear. We connect these 2 points with a line. Okay, with a line. And here, what we have a concentrated load, which is 8, and it goes down. Remember, if there is a concentrated load on shear force on the system, on the shear force diagram, there is a sudden change. Yes, let's do that change. It goes down 8. Okay, I'm at 11 and go down. Oops, the area. Let me clear this portion just a second. This line, I'm gonna draw a little large this portion. Okay, this is 21. At this portion, we have 11. So we go down 8. Okay, to this point, it's 3. Okay, we are now here at the right hand side of the 8. Now calculate this area in between these two concentrated loads. It's easy again. 2 times 5, 10 again, 10 again. Let's say the second point is this. We are gonna go down 10. 3 minus 10 minus 7. That's okay. We are gonna go to 7 in the negative side. Let me write that point here. 7. So how we are going to connect these 2 points? We're going to connect them with a line. Up. Up. With a line. Okay. But this portion is negative. This portion is positive. Now we are here. We are at 7. Minus 7. There's a concentrated load here. Minus 7 minus 8. And go down 8. Here. It's going to be 15. Okay. Again, this portion is negative. And there is another uniform distributed load portion here. Calculate the area or magnitude of that UDL. 2 times 5, it's 10 again. I'm here now at this point. I'm gonna go down again 10. So here 25. It's going to 25. Since this is the uniform distributed load, I'm going to connect them to each other with a line. Okay, and this is the negative portion. So that's okay. Let's have a look the column, the right column. What is the shear force on the right column? So let's cut the system from here. Vertical force is 25. When we cut the system, is this left cut or right cut? Take this portion and put next to it, and you are gonna see this is the left cut. That's why in the left cut it goes right, T. But is there another loading at this portion? No. So what is T here? T equals 0, because there is nothing which is perpendicular to frame. So that makes a shear force on the frame. So that's why T is 0, as you can see from this cut at this point. T is 0. Okay, take a look all the column. We are now here. Shear force is 0 all the way up to this column. Is there any other loading which makes shear force on the column? No. On this column, the axial force is 0. Okay, you can write this to the column. Now, this is the shear force diagram. It looks like a little bit complicated, maybe, but when you do these calculations by yourself, you're gonna see it's really easy. I'm not doing a complex thing. This is easier than other subjects. I'm just following some rules and just calculating area. Now, as you can see, we have the T diagram. What we are gonna do now, we are gonna do the moment diagram. So we will use the area under the shear force diagram. Okay, now let's do the moment diagram here. Okay. Here we go. So at this point, at this support point, we have a pin support. So moment is 0. This is my start point, by the way. Remember, the viewpoint is here inside. So inside is positive side for the moment, but no worries. Let's draw the diagram. Calculate this area. This area, what's it? 4, this is a rectangle, 4 times 3, the height of the column, which is 12. We are gonna add this 12 to this 0. So I'm gonna have a moment diagram 12 here. So how I will connect these 2 points to each other? Since this is a line, horizontal constant line, this will be, that means if this is a constant value, we are gonna use 1 degree curve on the moment diagram. So it's line. Let's connect these up. I couldn't do that. Let me do it with this. That's better. Okay. Okay, here we have 12 ton-meter. Is it positive or negative? Since this area is positive, this is positive, you know. Where we are at this corner, at the column side. When we go ahead the beam side, what was the rule for the frame corners? Remember, there was a rule for corners. The moment at each side of the frame equals to each other. if we have a positive moment here, same value positive at that corner. So we are going to start from positive 12 from here. At the beam, the moment, the start point at this point, moment is 12 again. We know that. Let's calculate this area. Okay. And also, we need to calculate this portion, this one where change here. You know, this distance totally to, let's say here, x, and this portion is 2 minus x, right? 2 minus x. And if you do this equation, I guess there is a similar, we are going to calculate this x from the similar triangles. X over 2 minus x equals 3 over 7. So x here, let me think about that. I don't have the number, but it should be, if here is 2, yes, 0.6 meter. Okay, it should be 0.6 meter. 0.6. Okay. Now we are going to calculate the area here and also this portion. You can calculate the trapeze area plus the triangle, small triangle over here. Okay, it's easy. It's 32.9, the total area here, 32.9. Now, what is our start point for the beam? This is 12. What we are gonna add, because it's positive, 32.9. So 32.9 plus 12, it's gonna be 44.9. And since the shear force is going from the 0, we are gonna have the maximum moment at this point. This 44.9 is the maximum loading here. Maximum moment, sorry. Maximum moment on the beam. Okay, this is positive. Now we have to calculate the area at the right hand side, which is the negative portion of the shear force diagram. This is a complicated area, but make it simple. Take into account this trapeze area and then this small triangle, because we know this portion, it's 1.4 meter. Okay. So calculate the area. Total area is here 44.9. So we have, it's minus, we are at the top of the hill here. We are gonna go down to 0 because the calculated area is same. At this portion, the total is, we are at the positive side, no worries. We go to the this 0 point. This is the moment of the beam. Let's have a look the column. If I have the 0 moment on the beam, I'm gonna have the 0 moment at the top of the column, right column, because remember the rule is rule. At the corners, at each side, we have the same magnitude moment and the same sign. The sign is same. If I have a positive 20, Yes, it's positive 20. If it's 0, it's 0, whatever. Now, the moment on the column at this point is 0. Okay. Is there any other moment on the bottom side? Let's have a look. If you can't see anything at this portion, since there is a roller support here, the moment is 0 at the bottom. So there is no horizontal force which makes a moment on the column. So that's why the moment on the right column is completely 0. So this is the moment diagram of this frame. Okay, it looks complicated, but please take a look at this question by yourself. Okay, firstly, again, listen this recording and then try to solve the problem by yourself. You're gonna see that it will be really easy because we are not doing a complication. Okay, this is not a rocket science. This is easy. We are just using the geometry and calculations. There are some rules. That's okay. There should be. If you follow these rules, you can solve every problem. By the way, don't forget to draw this portion to your page when you start to solve internal force diagram. Okay, please draw these positive directions. If you are not sure about the sign of the force, please cut the system over there and make the or write the equation and get the solution with sign. So, okay, next week is the Children's Day. You know, we don't have class, and the week after the next week we are gonna have our midterm exam. Okay, please take a look all these subject. If you are trouble, please send me an email. I'm gonna try to explain your question. That's all for today. Take care of yourself. Have a good weekend. Okay, bye bye.